So, welcome back to this lecture on sorting, where we are going to introduce the sorting problem and talk about our first sorting algorithm, which is going to be insertion sort. All right, so what is sorting? Sorting is a very common operation. I'm sure you've already done this once. Suppose you have a bunch of sheets of paper. Okay, you have a bunch of exams from students. Okay, let's say from students like Jack Smith, Jane, I don't know, something like Jane A. I'm not going to give names to everyone. John X, and I don't know, Jake B, something like that. So suppose we have a bunch of students, and we would like to arrange them in alphabetical order by their last names. All right. So what we really need is to first put Jane. Her last name starts with an A, followed by Jake, whose last name starts with a B, followed by Jack. Okay, I'm not very inventive in my names here, followed by John. All right. Maybe we could add a Bob in there. All right. I'm just being facetious here, but the point is, we would like to sort. So what does sorting mean? Sorting is a process of ordering. So you're given a bunch of inputs and you're given an ordering. So you're given a bunch of inputs, okay? And in computers, our inputs are going to be arrays. So, and let's take them to be arrays of numbers, because numbers are easy to write on the board. I don't have to invent names. I just have to invent numbers. All right, so we are given a bunch of numbers. All right, we're given a bunch of numbers, and I would like to sort them according to an order. Okay, so according to an order, in mathematics we would call this a total order, according to a total order. In this case, the order is just the less than or equal to relation. So I would like to sort them in ascending order according to less than or equal to relation. So the smallest number is 4, followed by 12, followed by 15, followed by 18, 19, 20, 21, 23, okay, and 45. I believe that's it. All right. So what are the requirements for sorting? What are the key requirements for sorting? So there are two requirements. Number one is that the output must have exactly same elements as inputs. So you cannot have a new element in the output array that wasn't in the input array. So every element in the input array is somewhere in the output array. You are only allowed to reorder things. You are not allowed to delete or insert new elements. And likewise, you cannot have an element here that wasn't in the input. So every element in the output is already in the input. So the input and output, it's only the only thing you're allowed to do is permute them. Okay, so only thing you're allowed to do is permute the array. You're not allowed to add new elements. You're not allowed to delete elements. Okay, that's the first requirement. The second requirement is output must be sorted according to the provided order. So if less than equal to is the order, then the output must be sorted in that order. So 4 must be less than equal to 12, must be less than equal to 15, must be less than equal to 18. So this is what it means to sort in ascending order. If you wanted to sort in descending order, instead of giving less than equal to as the ordering relation, I would have given you greater than or equal to. All right. So far I'm just going to talk about ascending order sorts, but descending order sort is very similar. Wherever you see less than equal to, make it greater than equal to. All right. So what is the sorting problem? So for the sorting problem, the input is an array A1, A2, and this is going to be another annoying convention where we deviate from Python in this class. Our arrays are going to start from 1 and end at n. Okay. So whenever you translate code from pseudocode that we will write, I will show you in a second what it means to write pseudocode. whenever you translate that, you better be careful that arrays move from 1 to n. Okay, so I'm going to write this as a of 1 or a underscore 1, a of n. And the output is going to be the same. It could be a same array, it could be a fresh array, but now the elements are sorted. Let me call them a hat of 1, a hat of 2, a hat of n. So what does it mean? For the set, or more importantly the multi-set, a hat of 1 to a hat of n must be the same as the set of elements a of 1 to a of n. You cannot have new elements come in. It must be the same set of elements. Okay, the set of elements must be preserved. The second thing is, and this is the same as requirement 1, the second thing is a hat of 1 must be less than equal to a hat of 2, must be less than equal to, all the way less than equal to a hat of n. So this is the second requirement here. All right, so you want to sort an array. How do you sort an array of n elements? Okay, now sorting is really common. Okay, where do you see sorting? Anytime you load an Excel spreadsheet, you can sort each column according to some criterion. So for example, if it's a column of strings, like so, you could sort them according to the last name. Okay, and there, instead of the order being the less than equal to among numbers, the order is the alphabetical order or the lexicographic order. So here the sorting order is the lexicographic order. Okay, I'm writing it in short for lex, which simply means it's the dictionary order. Okay, here the sorting is the increasing order given by the less than equal to relation. Okay, so not only can you sort numbers, you can sort strings, you can sort all kinds of objects. For example, you could overload. In many languages, you could do overload, operator overload, and you could overload the less than equal to or the compare operator. And once you overload this compare operator, you can call a generic sorting function. You can call a generic sorting function to sort objects, an array of such objects. So you could do this in Python, you could do this in C++, you could do this in Java. All of them have generic sorting functions that can not only sort numbers, they can sort strings, they can sort classes, they can sort whatever, they can sort dictionaries, but you need to specify an ordering relation. And once you do that, it just becomes a generic sorting algorithm that applies on that ordering relation. But for this class, we are only going to study numbers, arrays of numbers, and we will use less than equal to, so we will do ascending sort. All right, so what about sorting algorithms? So sorting turns out to be a well-studied problem. Number one, because it's so useful, we would really like to sort, and often we don't want to sort small arrays, we would like to sort large collections of data. So one of the things that doesn't get mentioned in big data is the need to organize big data, and for that you need efficient algorithms like sorting. All right, and so we need to sort large numbers of arrays. And so with this in mind, there are plenty of algorithms for sort. Okay, so the most common algorithms for sorting are, we will study them, insertion sort, which we are going to study now. There's something called bubble sort, which I will skip, but it's there in your book, you can look at it. There's something called merge sort, heap sort, quick sort. Okay, and then there are combination sorting algorithms that take different nice characteristics of these algorithms and do so. There's something called tim sort, which is considered to be the state of the art in sorting algorithms. It's implemented by many languages, including Python. All right, and these include many of the best characteristics of these sorting algorithms. All right, the one that's most commonly used these days is quick sort, insertion sort for small arrays. Okay, so typically a combination of quick sort and insertion sort. We will study this in this class in a lot of detail. Typically a combination of these two turns out to be the fastest sorting algorithm. And you can do much more sophisticated ones, but if you want to get a fast sorting algorithm done, you could do it through a combination of quick sort and insertion sort. But let's start by studying a simple sorting algorithm, which is the insertion sort. All right, so what is the insertion sorting algorithm? All right, and this we will study in the next lecture. All right, So we will start in the next lecture. We are going to study this first sorting algorithm, which is called the insertion sort. All right. See you then. Bye. Oh, welcome back. In this lecture, we are going to study the insertion sort, which is going to be the very first sorting algorithm we'll study in this class. Okay, so first let me give you the idea of insertion sort. In the previous lecture, we looked at what sorting means. So let's now look at the idea of insertion sort. All right, so the idea here is, suppose we are given an input array, let's say 2, 7, 4, 1, 3, 6, 5, and a 0. All right, let's say this is our initial array. All right, now what we are going to do is we are going to go through each of the elements of this array from beginning to end. All right, and what we are going to do in insertion sort is roughly we are going to do the following. So we are going to maintain two parts of the array. The first part of the array, which I'll draw in pink, is going to be a sorted. So it's going to look something like this: 1, 2, 4, 7. So this is going to be the part that's sorted. And then comes the part that's unsorted, let's say 3, 6, 5, 0. So here, for example, I would have sorted the first four elements, and the rest of the array is untouched. All right, and then each step of insertion sort is going to grow the pink region by 1. So extend the pink region by one more element. How does that work? All right, that works like this. So suppose the pink region now has the first four elements. So 2, 7, 4, 1 has been sorted. So the first four elements of the array have been sorted. So this is somewhere in the middle. All right, now the pointer comes to 3. So this pointer comes to 3. All right, so what happens is this is called the insert step. To grow the pink region by one more element, okay, I'm going to need to insert 3 into this array. How does 3 get inserted? Well, first I look for the right place for 3. I'll start scanning from the left, and I will see, okay, 3 needs to come here. All right, but because this is an array, if I'm going to insert 3 here, then 4 and 7 need to scooch over. They need to move over. So 4 needs to move one place to the left, 7 needs to move one place to the right, 7 needs to move one place to the right. And because we are mirrored over, to you it will look like one place to the left. All right, to me it looks to the right, to you to the left. All right, okay, all good? All right, so how does this happen? So in the insert step, there is two parts. First, find where 3 needs to go. Next, perform the insertion and move everything over. Sorry about the spelling there. Move everything over. How does that look? In this case, that looks like this. You would end up with 1 and 2, and then the new element 3, which I'll write in green, gets inserted. Everything else moves over. Okay, and now the sorted portion includes the first 5 elements of the array, with the remaining ones being, I'll write them in blue, 6, 5, and 0. Okay, and the pointer moves to 6. So 6 gets inserted next. What happens? Where does 6 get inserted? Again, the same procedure, A and B gets run all over again. And now, where does 6 get inserted? Well, 6 gets inserted right here between 4 and 7. That's where it's going to get inserted. How do I know that? I'm going to scan from the beginning of the array until I find an element that's larger than 6, and then I know 6 needs to get inserted there. All right, so how does that work? So then once I do that, I'm going to insert 6 there. So now I get a new array 1, 2, 3, 4, 6, and 7. Let me follow my convention and put a green thing under 6. That's the new thing that gets inserted, followed by 5 and 0. Okay, and 5 and 0, I should have written them in blue, but I'm simply going to put a blue box around them so that you know. All right, so this is the basic idea. So what is insertion sort? Insertion sort goes like this. Initially, the entire array is in blue, which means nothing is sorted, and then I start with the very first element. Okay, so when I start with the very first element, which is 2, it's just one element, so it's already sorted. Okay, one element, there's nothing to sort, it's already sorted. And then I have 7, 4, 1, 3, 6, 5, 0. And now 7 gets inserted. So 7 gets inserted, and when you scan, you find that 7 is already in the right place, and so therefore you trivially insert it by just keeping it where it is. So now you get 2, 7, and then the remaining ones are 4, 1, 3, 6, 5, 0. And then the pointer goes and points to 4. All right, and then in the third step, 4 gets inserted, and 4 should get actually inserted somewhere between 2 and 7. So therefore it becomes 2, 4, 7, and then 1, 3, 6, 5, 0. As you can see, the blue part remains untouched. The pink part is always sorted. So the first 3 elements are now sorted. Now the 4th element comes in. It has to go to the very beginning right here. So now you get 1, 2, 4, 7. Okay, and then the remaining are just the same, 3, 6, 5, 0. All right, and the cursor goes to the 3, and you can see some of the steps here, okay, following. So eventually what happens is when this algorithm finishes, you get 1, 2, 3. So you get 0, 1, 2, 3, 4, 5, 6, 7. All right, so the entire array gets sorted. All right, so this is the basic idea behind insertion sort. In the next lecture, I'm going to write down the pseudocode for insertion sort, and we'll actually first start by writing the pseudocode for the insert procedure to insert a new element into the array. And once we are done with the insert procedure, we are going to complete the insertion sort procedure as the pseudocode, and the lecture after that we are going to do the complexity analysis and measure the running time or study the running time of insertion sort. All right, see you then. Bye. Back, and now we are going to study the insert method for insertion sort. Okay, we are going to study the insert method. In the insert method, we are going to take an array A and an index j. Okay, and we are going to take, so we are going to assume that A has A of 1 to A of n. Okay, and somewhere in the middle is A of j. Okay. All right, j doesn't have to be n minus 1, so it's somewhere in the middle. So let me write some dots here. Okay. All right, so we have A of 1 to A of n. Okay, and now I would like to insert A of j, and we will assume it's very important, this is very important, that this is the part from A of 1 to A j minus 1. Okay, is sorted. Okay, so it's sorted, so I'm going to put a box next to it, like a pink box, and A of j is what we are trying to insert. All right, so this is to be inserted. All right, so the way I explained so far is you are going to look from the left to, or from your right to left. Okay, so it's remember I'm inverted, so we are going to look from one end all the way, find the insert position. So the way we said it so far is find insert position, and B, move elements over. Okay, As an example, suppose the array was, I don't know, 2, 7, 15, 24, okay, and the element to be inserted, let's say, is at 10. The rest of them don't matter. Okay, so here this is position number 1, 2, 3, 4, 5. So this is the array A, and j equals 5. All right. So I would like to do this. Right? How does it work? So the way we said is, let's scan the array from the beginning. Let's scan the array from the beginning. Find out where this element j needs to be inserted. And once we find out where it needs to be inserted, we can do a swap. All right. So we can do a swap. All right. So this is one way of doing things. All right. There is a more elegant way of doing things, which is, instead of looking for the position from the left, let us look for the position from the right and keep swapping as we move along. So how does this work? So this works like this. So let me start, instead of starting from 10, let me start already from 24. All right. Now 24 and 10 are in the wrong order. So let me swap them. So I'm going to use this operation called swap. Okay, a of I, a of j. So this is going to be a primitive operation. And in an array, you have a of I, position number I, a of j, position number j, and swap, let us say, exchanges these two elements. So if I swapped a of 4 and a of 5, in this array, then it's going to swap 10 and 24. All right. So here is what I'm going to do. I am going to keep scanning from the right. I'm going to keep scanning from the right. And as long as this 10 is in the wrong position with the element immediately to the, in my view, it's to the left, but when we flip the screen, it will be to your right. Okay. So as long as this 10 is in the wrong position to the element immediately before it, all right, we will swap. Okay. So how does the pseudocode for that look? So the pseudocode looks like this. So I'm going to try and write it in the pseudocode convention of the book. So remember, if you're translating this to Python code, in Python, arrays start from 0 to n minus 1. So you remember that. Okay. So I'm going to write down a for loop. What is this for loop going to be? For I going from j minus 1 down to 1. Okay. So this is an example of a for loop. This says, let I run from j minus 1 all the way to 1, and unlike Python, whenever I write for loops in pseudocode, both ends are inclusive, which means that it's going to start from j minus 1, go all the way to 1, do 1 and end. Okay, so it's not going to end at 2 like it does in Python. It's going to actually end at 1. Okay, so the right hand side and the left hand side are both going to be included in the range, unlike Python. Okay, so this is the pseudocode convention. And it's meant to be free of language barriers. So if you should translate it to Java or Haskell or Python or Scala, whatever you want, but we are going to write it in this convention. All right. And this is the convention of the book, so I'll stick to it. So what is I? So I is this pointer. Okay, and j is going to be at 10. All right. So I is going to start from j minus 1. So if j is 5, then it's going to start from 4, 3, 2, and 1. All right. Now what am I going to do? So here, so far what do I have? So in the first instance, j equals 5, okay, and I equals 4 in this example. So I have 10 and 24 and 10. So if a of I, okay, a of I is actually, so let's look at a of I and a of I plus 1. So if a of I is greater than a of I plus 1, if they are in the wrong order, then swap a of I plus 1. Just swap them, just exchange places. Else, if a of I is in the right place with respect to a of I plus 1, then return or break. So break exits the loop and we return. All right. What is this doing? So instead of iterating from the left like I described before, which makes sense for us, we are doing it from the right, and we are changing positions as we go along. So this is like a dual purpose loop. Okay, not only does it find the right position for j, for the element I want to insert, I claim that it also magically inserts it and moves the other elements out of the way until it finds the right place. Okay, let us see how it works on this example. Okay, so on this example, we have the array. We are trying to insert the element at position 5. All right, so let's write down a table. Let's write down the array and see what's happening. Okay, so j is always going to be fixed, and it's going to be 5. Now I is going to run from 4, 3, 2, and 1. Very good. Now when I equals 4, what is a of I? A of I is 24, and a of I plus 1 is 10. So a of I is 24, a of I plus 1 is 10. Am I right? Okay. Now 24 is greater than 10. 24 is greater than 10. So what it ends up doing is it swaps the two places. All right. So it swaps 24 and 10. So the new array is going to look like 2, 7, 15, 10, and 24. And I'm going to put a box around the 10 so that you know that it's actually in the wrong position. Okay. And now I becomes 3. So I becomes 3. So what is a of I? Is a of 3. A of 3 is 15. A of I plus 1 is a of 4. Look here. So 1, 2, 3, 4. It's 10. Okay. And so what's going to happen? A of I is greater than a of I plus 1. So swap. So when I swap, now I get 2, 7, 10, 15, 24, blah, blah, blah. All right, let me put a box around the 10. All right, now I goes to 2. When I goes to 2, what is a of I? A of I is a of 2, which is 7. A of I plus 1 is 10. Now what happens? Now the if condition is no longer true, so we fall into the else condition. So what are we saying in the else condition? In the else condition, we are saying that we found the right place. So now we just break. We just return out of the loop. And in fact, we are done. So in this example, by moving from right to left, I was able to both move elements out of the way, move things to the right, move the array, move the element I want to insert to the right position. And remember, when I say right and left, I'm actually mirrored over when you see me, so it's going to be the opposite for you. But at least you get the idea of what I'm talking about, right? So you're moving elements to the right position, and you're moving the other elements out of the way, all in the same loop. And you, if you find that the element is already in the right position, you don't have to do the rest of the loop. You can simply break. All right, and this is the insert procedure. So this is the insert procedure. All right, now that we have the insert procedure done, we can do the rest of insertion sort. What is insertion sort? Insertion sort is simpler. For I going from 1 up to n being the length of the array. So here 1 and n are both inclusive. Okay, insert a comma I, and that's it. Okay. In fact, to avoid confusion, let me call this j and j. That's it. So move from the beginning of the array to the end and insert. All right. And this is the whole of insertion sort of an array A. All right. Exactly as I described in the previous lecture, now we have written the pseudocode. Remember, there are some pseudocode conventions that are going to be different from Python. So if you translate the code verbatim, it's going to crash. One difference is we are going to assume that arrays start at 1, end at n. We know that loops, for example, we are going to write these funny loops, up to and down to loops, where both the ends of the loop are inclusive. All right. And those are, whenever there are differences between Python, I will try and point them out as we go along until you know these differences and you're careful implementing them in Python. All right, so that is insertion sort in a nutshell. The next lecture, we're going to look at the important question of how long does insertion sort take in the best case, in the worst case. All right, let's talk about that in the very next lecture. See you then. So in this lecture, we're going to look at the complexity, or what is known as the computational complexity of insertion sort. Now, what is computational complexity? Computational complexity is a fancy term for just saying how much does it cost, okay? How much does it cost? And in computation, we look at cost in terms of resources consumed, and the two important resources are time, how much time does it take to run, and space, how much memory does it occupy, because these are going to be bottlenecks for running this code on large inputs. Now there is already a problem here. When you are going to measure time, you are really interested in measuring time on a particular machine, but we are not designing this algorithm to run on your laptop, my laptop, on a server. We are not specifying how the algorithm runs. So time is going to be a function of which processor I choose to run. And therefore, the time that I measure today is going to be way faster than the time I measure 6 months ago, not because the algorithm changed, not because I improved things, but just because the processor got faster because of some other advances. So I need time to be measured in a way that's independent of the processor, the clock speed. I don't want to say on a 1.8 megahertz processor running the Mac OS operating system with this much cache and this much RAM, it took this much time to run. That's too much details and too complicated. I want a way to measure time that's independent of the processor that's being run. I also want to measure space complexity, which is the memory. But then the memory usage depends on how big these numbers are, whether it's a 32-bit computer or a 64-bit computer. So I want to simplify it. I also want to make it independent. So this is number one, challenge number one. Challenge number two is this algorithm is not going to take the same time on all the arrays. So there are certain arrays in which it's going to run faster and certain arrays in which it's going to run slower. So there are some best cases and some worst cases. And so I need to be confident that I know what the turning time is going to be in the best case and in the worst case. All right? And therefore, we call the best case as the best case complexity and the worst case as the worst case complexity. Okay? So, and usually we are interested in worst case complexity because the best case complexity is too self-serving. It's often considered too self-serving. And then there's a third one called the average case complexity, which we will revisit when we have a better grounding in probability. All right, so we are not going to visit average case. All right, so what is, how do we make the whole thing independent of time? All right, so to do that, we just need to give some abstract cost to certain operations. So I can say comparison takes one time unit. I don't know how much that time unit is, but let me say comparison takes one time unit. Let's say swap takes one time unit. Or if you want to be more precise, you can call it C sub 1 time unit. And let's say a swap takes C sub 2 time units. Okay? And let's say running a for loop, each iteration of the for loop, what does each iteration of the for loop do? It decrements I by 1, starts I with j minus 1, ends with j. So let's say each iteration costs C3 time units. All right? Okay, so having said all of that, what is the cost of an insert? All right? So what is the cost of an insert? It depends, right? So there is the best case for insert and there is the worst case for insert. What's the best case for insert? So I'm just studying insert and then I will study insertion sort. What's the best case for insert? The best case for insert happens when you enter this loop. The moment you enter this loop, you check this condition, it's immediately false, and you break. Okay, let's say break costs C3 time units, something like that. All right, so this is going to be the best case for insert. When does that happen? That happens in this very specific situation. So whatever you're trying to insert, let's say now you have some elements A1, A2, AJ minus 1, A sub j. So this is already sorted in insertion sort. Okay, we assume it's already sorted. Now when you're trying to insert A sub j, this situation happens ai greater than a minus ai plus 1 is false, which means in this case a sub I less than equal to a sub I plus 1. So what happens can be that aj is larger, okay, so aj is larger than aj minus 1. So I'm going to write a less than equal to, in which case aj minus 1 is less than equal to a sub j. So if the jth element is already greater than equal to j minus 1, which is when you get to break, what it means is that aj doesn't need to be inserted. It's already in the right inserted place. So if it's already in the right inserted place, then no work needs to be done, right? Or some nominal small amount of work needs to be done. The for loop immediately exits. All right, how much is the best case then? So the best case is going to be something like C3, the cost of doing one iteration of the for loop for bookkeeping, C1, the cost of doing this compare, plus I think I should have called this C sub 4 because C sub 3 is already being used. Let me call this C sub 4, no problem. All right, so this is very, very simple. And later what we are going to do is we are going to call this theta of 1 or O of 1, big O of 1. So when we get to the big O, big theta notation, which you must have already studied in your basic discrete math class, you would just write it as big theta 1 or big O 1. It's a constant. That is the extent to which we care about it. And that's how we achieve independence, by using the big O, big theta notation and not worrying about constant factors. All right. Good, that's the best case. And as I said, who cares about the best case? It's a little bit too self-serving, right? What's the worst case of insert? What's the worst case of insert? Worst case complexity. What's the worst case of insert? Well, the worst case is when this iteration has to go all the way from j minus 1, j minus 2, j minus 3, all the way to 1. When does that happen? That happens when aj's insert position is at the very beginning of this array. Okay? If aj's insert position is at the very beginning of this array, that's when the worst case happens. So what's the worst case complexity? Well, in the worst case, this entire loop runs j minus 1 times, j minus 1 down to 1. It runs j minus 1 times, and each time it runs the compare, it runs the swap, and it runs the for loop iteration, whatever bookkeeping is needed for a for loop. So here the answer is, and by the way, there needs to be, okay, so the answer here is going to be j minus 1 times C1, which is the cost of doing the compare, plus C2, the cost of doing the swap, plus C3, the cost of doing the for loop. So the worst case is j minus 1 times this. And when we are back next week to doing the big O, big theta notation, we are simply going to write this as big theta of j or big O of j. Big O of j is the upper bound, big theta of j is the exact answer. All right. So in this case, it's actually big theta. That's a better thing to say. You can also say big O. And we'll see this next week. Don't worry about it right now. But I think you've already seen it, so I'm just giving you the a flavor of it. So this is the computational complexity for insert. In the best case, it immediately exits with a very, very small cost of just 3 operations. In the worst case, it runs j minus 1 times, and the complexity is something like j minus 1 times C1 plus C2 plus C3. Okay? All right. What are we going to do next? Next, let's look at insertion sort. Now, what is insertion sort doing? It's running insert n times from j equals 1 to n. What is the best case complexity for insertion sort? In the best case complexity, each insert operation immediately exits in one iteration. Each insert tickles the best case. If each insert tickles the best case, then you get the best case overall for insertion sort, and the best case would be n times the complexity of the best case for each insert, which is C3 plus C1 plus C4. What kind of an array happens to solve for this best case? Okay, and the answer here is simple. You will notice that the best case only happens if the array is already ascending sorted. So if your array is already sorted in ascending order, you will find that the best case of insert happens all in every call. So the entire sorting is done within n times. N is the number of times this outer j loop runs, times the cost of each insert, which is C1 plus C3 plus C4. But again, best case is too self-serving, so we really don't worry about the best case. Too self-serving. So if I was about to sell insertion sort to you, and I only talked about the best case, you might sue me and say, hey, in the worst case, you are so much worse than you advertise. So best case, usually we don't do the analysis, but though to contrast it with the worst case, I really like to have the best case analysis as well. What's the worst case? Well, the worst case is I run this insert, but each time I run it for each j, I tickle the worst case complexity, this guy. Okay, and this is going to be summation j going from 1 to n, j going from 1 to n, and this is the worst case. Summation j going from 1 to n of what? Summation j going from 1 to n, the cost of doing insert with j in the worst case, which is j minus 1, C1 plus C2 plus C3. So this is nothing but C1 plus C2 plus C3 taken out in common of 0 plus 1 plus 2 all the way to n minus 1, because j minus 1 summing up from 1 to n. So this is n times n minus 1 over 2 times C1 plus C2 plus C3. And then once we are ready with our favorite big O notation or big theta notation, this is simply big theta n squared or big O n squared. And we are going to talk about this in the very next week. Okay, so we are going to get to the big O notation, and remember, that's how we are going to achieve this independence from the machine that you're running this algorithm in. So in the worst case, the algorithm runs something like n squared, n into n minus 1 by 2 times C1 plus C2 plus C3. In the best case, it's n times C3 plus C1 plus C4. Also, what is the array that causes always the worst case of insert to happen? Well, if you think about it, you would notice that an array that's descending sorted, that is sorted in exactly the reverse order that you need it to be. So if you want it to be sorted in the ascending order, suppose I give you an array that's sorted in the descending order, that's always going to give you the worst case of insertion sort. Reason being that each element aj, when you insert, needs to go all the way to the beginning because the array is descending sorted. So each element aj will need to go all the way to the beginning, so it needs to move. Okay, and that's a problem because each time I call insert, I'm going to end up running this loop entirely from j down to 1, which gives me a complexity that's n into n minus 1 over 2 times this, if you want to be really precise. And what we will do is such precision achieves nothing for us, so we will simply call it n squared and be done with it.